So we left off on Friday talking about aromaticity, and we were looking at systems that contain carbons, and we're going to look a little bit further today for systems that have more than just carbons in them. So aromatic compounds fulfill 2 to 3 main criteria. We have to have a fully conjugated ring with overlapping p orbitals completely in the full ring, so it has to be conjugated, otherwise the p orbitals won't overlap. And it meets Huckel's rule, which is an odd number of electron pairs, or 4n plus 2 pi total electrons in the overlapping pi system. And anti-aromatics are also fully conjugated ring with overlapping p orbitals, but they have 4n pi electrons. And they're extra unstable, whereas aromatic are extra stable. Everything else is just non-aromatic. So we're going to talk about other types of systems than just the straightforward benzene. So let's look at this system. Looking at this system to figure out if it's aromatic or anti-aromatic. All of the carbons in this particular system do participate in pi bonds, so we have completely overlapping cyclic system of p orbitals. But if this double bond in the center isn't participating in the overlapping pi system, it's in the middle, it's not in the ring, then this particular system has only 14 pi electrons that are in the closed loop system, and therefore that does go with 4n plus 2 pi. So this is an aromatic system, and of course this would have to be planar for it to be aromatic. A term for a ring that are fully conjugated is annuline. Benzene is part of that. We don't typically talk about it as 6-annuline, but it could be considered that 6 pi orbitals, but that's the same as our benzene. But 10-annuline and 14-annuline are also considered a fully conjugated system. But some annulines are aromatic while others are anti-aromatic. 10-annuline is neither, however. And the reason why is because if we actually look at what this looks like, these 2 hydrogen atoms prevents the ring from being fully conjugated. Because those 2 hydrogen atoms prevent the ring from being planar. So because these 2 hydrogens are there and they have to be pointed in, remember, we don't have free rotation around these bonds. So what we have is this trans double bond, and this hydrogen has to be pointed up because we do have that trigonoplanar geometry. So with this trigonoplanar geometry in this one, those 2 hydrogens prevent the ring from being fully planar. And since it's not fully planar, that means it can't be conjugated, so it's actually a non-aromatic system. With our 14-annuline, we don't have that problem because of the geometry. But 10-annuline is special, it doesn't allow it to be planar. So again, it has to be planar for it to be aromatic. Also, some rings can be aromatic when they carry a formal charge. If we take into account this 5-membered ring with a negative charge, remember that our lone pair can be in an unhybridized p orbital, so that means that we do have a fully conjugated system. If we look at the diagram of this compound, again, remember when you're drawing these frost circles, the point of the ring has to be pointed down, otherwise it won't represent what the molecular orbital diagram looks like. So with the point pointed down, we actually have a total of 6 pi electrons. Our 2 electrons of our lone pair and our 2 electrons in our pi bonds. There's still 6 pi electrons though, because those 2 electrons in the lone pair are in an unhybridized p orbital. They are completely in conjugation. So if we look at this compound is not aromatic. It's what we would say non-aromatic because we do not have a p orbital right there. So we don't have a cyclic conjugated system. And also when we're not fully conjugated, this doesn't have this molecular orbital diagram. But when we have these 6 pi electrons, we see the same aromatic system and the same sort of trend when we look at our Frost diagram that we did with benzene, meaning that our HOMO is low in energy, it's in the bonding orbital, and it's completely filled. So because of that, typically our sp3 carbon is not very acidic. It's really hard to deprotonate. But when we do deprotonate one of those protons, it causes the compound to be aromatic, and we see that reflected in the pKa, where the pKa of this hydrogen is much lower than a typical hydrogen, even one that would be in conjugation as far as resonance is concerned. So we have those resonance structures. We could draw our resonance structures where our lone pair is being pushed around the ring. And that's all of our resonance structures there. So we see that reflected in the pKa. Typically, an sp3 hydrogen carbon, pKa is around 50, and this pKa is 16, about on par of what typical alcohols are. And that's because that when we deprotonate it, the resulting compound is aromatic and has that extra stability. So even more than just electrons that are in resonance. And we definitely see that reflected. So that particular compound is much more acidic than normal because of aromaticity that's formed. If we look at a 7-membered ring, the charge can also be, a charged compound can also be aromatic, but in this case, the charged compound would have to hold a positive charge. Remember that carbocation is an empty p orbital. That still means that we have a cyclic ring of unhybridized p orbitals. So even though we don't have any electrons in this system, this is still a closed loop of shared electrons because this is an unhybridized p orbital and so are all of these. So if we look at this, how many pi electrons do we have in this system? We have 6. Remember, this is empty p orbital, and then we have 2, 4, 6. So we only have 6 pi electrons in this system. Again, when we draw our Frost circle, our carbon has to be pointed down, which is the case here. So when we draw those in, just like benzene, our HOMO is lower in energy and completely paired. So this is a super stable carbocation because when the carbocation forms, we form an aromatic stability. Aromatic compound is formed when we have that charge. So in fact, this particular compound is more stable in its charged form than its neutral form. Because in the neutral form it would be non-aromatic. We would not have that closed system because that carbon would not be an unhybridized p orbital. And of course we can draw the resonance structures for this, but the stability goes beyond just the fact that we have multiple resonance structures. It's because this is aromatic. Heteroatoms, other than carbon and hydrogen, can also be part of the aromatic ring. If we look at these cases, we have pyridine and pyrrole. And remember that nitrogen has a lone pair, but the lone pairs may or may not be participating in the aromaticity. It depends on the compound. So if the heteroatom's lone pair is necessary and the p orbital is empty, then it will be included in the Huckel pi number, but it might not be. So in the case of pyridine, the lone pair is not in the unhybridized p orbital because the unhybridized p orbital is already participating in a double bond. So with pyridine, that compound is aromatic. It has 6 pi electrons, but the lone pair is not participating in aromaticity. And we'll see that because this lone pair is still pretty basic. pyridine can be used as a base easily. We've talked about pyridine before. For example, when we took our tosyl chloride and reacted it with an alcohol, we usually use pyridine, which is a base. Those electrons are still available as a base because the electrons are not participating in aromaticity. When nitrogen gives up its electrons as a base, it's still going to be aromatic because the aromaticity is coming from the 3 overlapping pi bonds. Because remember, how many electrons can each orbital hold? The maximum number of electrons for an orbital. When we fill in the diagram, how many electrons do we put in a space? 2. Every orbital can only hold 2 electrons. So, if this unhybridized p orbital is already participating in a double bond, then this lone pair can't be participating in the aromatic ring because it's already full with its 2 pi electrons. Just like when we talked about whether a pair of electrons in chapter 1 was isolated or in resonance. And we talked about it being localized or delocalized. If the p orbital is already full, then the lone pair must be localized. And in this case, the lone pair is localized to the nitrogen, and it's not participating in aromaticity. That compound is aromatic, but it's these 6 pi electrons in the p orbitals. But conversely with pyrrole, we don't have a double bond between the carbon and the nitrogen. So if that lone pair is not participating in resonance, then that nitrogen would not have an unhybridized p orbital. So in the case of pyrrole, the lone pair is participating in the aromaticity. And remember, aromaticity will make the compound more stable, so it's going to act like that. So here, our double bonds are here. So for this compound to be aromatic, the lone pair has to be part of the system. So we have 2, 4, 6 pi electrons still. Because otherwise that nitrogen would not have an unhybridized p orbital. And we actually see this affect pyrrole's ability to be a base. It's not very basic because if it gives its electrons to act as a base, it loses aromaticity. So it's not going to act as a base very easily. And we can see that with our pKb. So if you notice with pyridine, because the electrons are not participating in resonance, when pyridine gives up its lone pairs, it's still aromatic, so it can act as a base pretty easily. But when we look at this structure, here this lone pair is participating in aromaticity, and then here it's no longer aromatic. In fact, this structure would be anti-aromatic, because now we only have 2, 4 pi electrons and a closed system of 1, 2, 3, 4, 5 p orbitals. So this particular structure is extra unstable, and we see that related in its ability to be a base. In fact, it won't act as a base very well, and the equilibrium lies in the starting material. So this particular compound is very acidic. When it loses a hydrogen, it forms an aromatic compound. If the lone pair is participating in aromaticity, it's not available to react as a base, as a nucleophile, as whatever. Because once it would, then we lose aromaticity. And we see that often with this one. And we can see this with the localization of the electrons as well. Again, that lone pair is localized to that nitrogen because it can't be in the unhybridized p orbital in conjugation with the double bonds because it's already full, that p orbital. But if we look at pyrrole, the electrons are not localized, it's delocalized around the ring in the aromaticity. So remember, to act as a base, the lone pair has to be given up. The lone pair is part of aromaticity, it won't want to be given up because that will result in a less stable compound. And we always want our final product to be lower in energy than our starting material for the reaction to be spontaneous. So let's look at these. Assuming both of these are planar, because it's hard to predict whether something is going to have the ability to bend out of plane or not if it's anti-aromatic. Though typically if a compound can bend out of plane to not be anti-aromatic, it will. But it's going to be hard for you to predict that, its ability to do that. So assuming that they're planar, let's figure out if these two compounds are anti-aromatic or aromatic. So looking at this first compound, we do have a closed system, we have in this case, we have 8 unhybridized p orbitals. How many total pi electrons do we have in that closed system? We have 8. We have our 2 electrons in our double bond. So we have a total of 8 pi electrons. In this case, the lone pair is not participating in that. Why? Yeah, our carbon-nitrogen has a double bond. That p orbital is already full. So that lone pair is localized to the nitrogen, not part of our aromatic or anti-aromatic system. So what we have is 8 pi electrons. 8 pi electrons is an even number of electron systems, so this would be anti-aromatic, unless if the compound could bend out a plane and be non-aromatic, which would be hard for you to predict. So if I gave you an example like this and I said this compound is showing that it's non-aromatic, explain that to me, you would explain that so it's not anti-aromatic, it bends out a plane. But I want to ask you to predict that. Or if I asked you to predict if something was aromatic, non-aromatic, or anti, pay attention to whether I put something like it's bent shape or not planar. Because if it's not planar, it's non-aromatic. So I would have to indicate that somehow. You're not at the level to predict that. So it would be anti-aromatic unless it could bend out of shape. If we look at this one, this oxygen has 2 lone pairs. And it can have an unhybridized p orbital if the lone pair is in conjugation with our ring. In this case, here, only 1 electron pair would participate in resonance because unhybridized p orbital can't have 2 electron pairs in it at any given time. And remember, look back at chapter 1 if you need to. An atom will only have 3 unhybridized p orbitals, but they're not going to be in the same plane. So if we have 1 unhybridized p orbital, that's more common. Usually we have hybridization. But either way, even if we had all 3, they would be in different planes. And only one of those unhybridized p orbital can be in the planes with the other. So what we have is, again, an 8 pi system. This system would be anti-aromatic and pretty unstable. And likely, the question is it more unstable to be anti-aromatic or more unstable that neither of the electrons are in resonance? And that's hard to predict, again. So it would just be predicted to be anti-aromatic. So to avoid that, it might remain sp3 unhybridized, but then none of the electrons would be in conjugation and in resonance. So it's hard to predict whether that's more stable than it being anti-aromatic, and you're not going to be expected to do that. So we would predict that it would likely be anti-aromatic with 8 pi electrons. Now if we look at this example, this one has 10 pi electrons and it's a fully conjugated system. So this one would be aromatic with the assumption that, of course, it can be planar. And we're going to assume that it would be. If we look at the next example, we have this unhybridized p orbital, but it's empty. So we don't have any electrons there. So we actually have a system that, again, has 8 pi electrons. It is fully conjugated, so we would call that one anti-aromatic. Now remember, if this didn't have a charge, it would just be sp3, and it would be non-aromatic because we wouldn't have a fully conjugated system. So it's just the fact that it has a charge that even allows us to have that unhybridized p orbital. If there's no charge and it's a carbon, then it won't have any aromaticity. So if we look at these, A is a completely cyclic system, but we would have 4 pi electrons, so that would be anti. And with this 3-membered system, it couldn't bend out a plane because we really don't have any space for that. If we look at B, this is a 6 pi electron system, and it's going to be fully conjugated. If we look at C again, this is sp3, so that's non-aromatic. because we don't have a fully conjugated system, because this carbon does not have an empty p orbital. So that one we don't even have to count how many pi electrons because it doesn't matter. It's not a cyclic system. D is a cyclic system, but we have 8 pi electrons total. These two and our 2 in each of our double bonds. So this would be anti. So our only aromatic is B. And you should be able to represent whether they're anti, non-aromatic, anti, or aromatic. So this one's non. Anything that's not anti-aromatic or aromatic would be non-aromatic. Polyatomic compounds can also be aromatic, usually known as polycyclic aromatic hydrocarbons, or PAHs, which you might see sometimes in products. You might see that term. They are known to be pretty stable, though all of the rings in the system may not be stable. So these are compounds that have multiple benzene rings that are connected together pretty much. We have naphthalene, anthracene, phenanthracene. Those are 3 examples. And each of those are made up of aromatic benzene rings. So they are considered totally to be aromatic. They can be shown that they're aromatic by showing that they have lower heats of hydrogenation, meaning they're more stable compounds. If it's a large number, that means we release a lot of heat upon reacting, so therefore they're less stable when we start. And what we see is that benzene, we know it's more stable than we expected it to be for its aromaticity. But for these, this is the stabilization total energy. This is the average stabilization per ring. So what this is normalized value. Because we have more pi bonds in these examples than we do in benzene, what we did was normalize it to where we're comparing each 6-membered ring as opposed to the whole system. Because of course it's going to take more energy to hydrogenate more double bonds. The more double bonds you have, the more hydrogens you need to add. So this is just normalized. And what you see is not only do we have the same comparable aromatic stability as benzene, but these systems are typically just a little bit more stable than benzene overall. Now that's the average structure. Sometimes all of the rings won't be as stable in a system. So the energy per ring is actually dependent on the structure of the compound. So if we actually look at the individual rings, for example, in anthracene, it's easier to react these 2 double bonds, so it's easier to get reactions at those carbons than the outer ones. So not all of the rings are necessarily as stable, but overall, all of these systems are considered aromatic because they're made up of connected benzene rings, and benzene itself is aromatic. That's an easy way to think about it. But sometimes the middle rings are more reactive. So they do still agree with Huckel's rule, even though technically Huckel's rule shouldn't be applied to them. But they all agree. We have 10 pi electrons there, 14 and 14, and that all agrees with 4n plus 2 pi. And these systems are completely planar. In fact, what we see in things like graphene, which is a bunch of benzene rings strung together, are very, very useful, typically in electronics. Because when we have all these overlapping unhybridized p orbitals, that means that electrons can be, electricity can be put through these compounds. So they're a good conductor of electricity, and you see a lot of graphene compounds in electronics to make them work well. Also, benzene rings have been used in things like solar cells to harvest light energy as part of that. So they're pretty cool compounds. So let's look at some of these. This one, is this one aromatic, anti-aromatic, non-aromatic? It's non-aromatic. Why? It's not a fully conjugated system. We have an sp3 carbon. What about this one? This one would be anti. We have 4 n pi electrons, so it would be anti-aromatic, assuming it's planar. What about this one? That one would be aromatic. What about this one? We have 8, so it's anti-aromatic. It is a fully conjugated system, though. What about this one? That one's aromatic. It has 10 pi electrons. What about this one? How many pi electrons do we have? 6, so that one is aromatic. It has 7 p orbitals, but when we're looking at Huckel rule, we're using the amount of electrons in those orbitals. And this orbital is empty, so that means that we only have 2, 4, 6 electrons in those 7 orbitals. So we're not counting the amount of orbitals, we're just making sure that they're all conjugated with p orbitals. And what about this one? How many pi electrons do we have? We have 2, 4 in can be 0. Because we do have a fully conjugated cyclic system. We have 3 carbons that are in a circle, that are in a ring, and they all have unhybridized p orbitals. So this one is, in fact, aromatic. Now, it wouldn't be aromatic again if this didn't have that positive charge, because then it wouldn't have a p orbital. So you have to have that unhybridized p orbital in the cyclic system. So when we looked at this one, all of these are actually aromatic. This one has 14 pi electrons. Assuming it's planar, I would have to tell you if it wasn't. If we look at this one, remember only one of these lone pairs can be in conjugation at a time. So this actually only has a 6 pi electron system. The other lone pair is not in the p orbital. So it's not part of the system. It's localized to the sulfur. Only one of those electrons is delocalized. So overall, we only have 6 pi electrons because 2 lone pairs can't be localized, can't be delocalized at the same time on one atom because that p orbital only holds 2 electrons. And of course, this one has 10 pi electrons, so that is aromatic. So now that we know how to determine if something is or is not aromatic, now we're going to talk about reactions. We're not going to be looking at any reactions of the aromatic ring. We're going to be looking at reactions on side groups. That's not true. We're going to look at 1 or 2 reactions of the ring. But in the next chapter, we're going to be looking at specifically reactions of benzene. So the first thing we're going to talk about is the benzylic position. Now, technically, this position is very similar in other aromatic species, but we're really going to be focusing on benzene for the rest of this chapter because it's the most common aromatic compound. Though, in all technicality, other aromatic groups that are directly attached can see the same type of reactions. But we're really just going to talk about benzene. So the position, the carbon position directly attached to the benzene ring, that's our benzylic position. Very similar to our Leydig position, except benzene's next to it except for just one double bond. So a carbon that's attached to the benzene ring is our benzylic position, and it's more reactive because of where it is next to the benzene ring than most carbons. And we will explore reactions of the benzylic position. So we already know that if we try to oxidize, double bonds don't really oxidize. And sp3 carbons that don't have any functionality on them also don't oxidize. If we have an alcohol, we can oxidize that to a ketone or a carboxylic acid. Or if we use PCC, we could stop at the aldehyde. But if we had these compounds, we wouldn't get any reaction because there's no alcohol there already. So we all of the times that we use our chromic acid, we already had an alcohol. So we changed the oxidation state. And that's generally true, except for the benzylic position. The benzylic position will react with a strong oxidizing agent like chromic acid. It's only going to react with the benzylic position, and it's going to form a carboxylic acid every time. The rest of the OR groups that was there, it gets cleaved and becomes a byproduct that we have to remove. So it doesn't matter what this looks like, we're always going to form the carboxylic acid. The benzylic position is especially reactive, even though we don't already have an alcohol in that position. There is one limitation. The benzylic carbon must have at least one hydrogen. If there are no hydrogens in that benzylic carbon, no reaction will occur. Otherwise, no matter what it looks like, it's going to form the carboxylic acid. This won't happen with a cyclohexane. So again, it's really, really important that you draw all of the electrons, all of the double bonds in the benzene ring. Because if it's a 6-membered ring but it's not benzene, we won't get this reaction in the carbon that's directly attached. This is a very special reaction. It has to be with benzene. So if we look at this example, we don't have a hydrogen in the benzylic position. This is our benzylic position. We don't have a hydrogen there, so we won't get a reaction. As long as there's one hydrogen, the reaction's always going to be the same. Potassium permanganate can also be used as an oxidizing agent. Came in a form with H2O and heat. You have to be careful with it because it's very, very reactive. So it'll react with a lot of different functional groups, which is why it's only really used if there's no other functional groups present. But it will also do the same. It'll form the salt, and then water at the end is there to protonate it to the carboxylic acid. So it's very reactive. So either KMNO4, water and heat, or our chromic acid, they will all oxidize to the carboxylic acid, as long as we have one hydrogen in the benzylic position. Again, this compound, with our oxidizing agent, nothing's going to happen, because this is not benzene. So if you do not draw the double bonds in your ring, your answer is wrong. Very wrong. It might not seem like it's very wrong, but reactivity-wise, it's very wrong. Because that does not react the same as benzene. So no reaction would occur with that. It has to be benzylic. So if we look at this one, A, nothing's going to happen. Where'd that extra carbon come from? Again, I have no carbons here. So there can't be any carbons in this final product that is an addition. Because I didn't put any carbons in. Where would those carbons be coming from? So that first reaction, A, is not a reaction that can occur. Because we don't have a benzylic position. We don't have any carbon there. B will work. C, this is not benzene. You cannot add carbons that you did not put in. And then D, we don't have a hydrogen. So we would also get no reaction for D. So B is the only one that would give us a reaction. And the byproduct, again, would just be washed away. It doesn't matter what this looks like. This can have 50 carbons attached. We're still going to form the carboxylic acid. We can apply this to synthesis. So our position, our benzylic position, are similar to our allylic positions as far as reactivity. We already know that that radical is more stable because it's in conjugation with the benzene ring. Though, I will note that even though you have multiple more resonance structures in the allylic position, our most stable resonance structure is this one, because these resonance structures break the aromaticity. So they're still contributing, but they're not as contributing because they're not as stable because the compound isn't aromatic in those resonance structures. So we don't have as much stabilization from having these multiple resonance structures as you might think, but it's still stabilizing. So the benzylic position reacts really well through radical bromination, and we've seen that before in chapter 11. That one's also true. We typically use NBS, but in this case, unlike with the allylic position, addition isn't really a concern, because if we did just use Br2, we still wouldn't get addition to the pi bonds, because that would break the aromaticity. But NBS is still typically used as a source of your bromine radical. Once the benzylic position is substituted, that's going to be our most stable position, we can do a lot of transformations. We can do SN1 reactions. And this SN1 reaction is more stable than most because, again, the carbocation that results in SN1 reaction is going to be stabilized by resonance. So this is a much stable carbocation than typical carbocations. Whether it's, in this case, it's shown as tertiary, but it doesn't necessarily have to be. Again, you have a lot of resonance stabilization, but not necessarily as much as you would think, because, again, you're breaking the aromaticity up a bit. But it's still aromatically, it's still stabilized by resonance. We can also have the SN2 reaction if the benzylic position is not sterically hindered. But even with this one, you can actually have a SN1 reaction with the primary carbocation because of resonance. So you can force any benzylic position to go through an SN1 reaction because of the extra resonance stabilization. But SN2 works as well. You can undergo an E2. You're going to form the conjugated double bond to the ring system, and that is going to be an even more stable double bond than normal because of the conjugation with the ring. This does not make this compound any less aromatic, because this pi bond is not participating in the closed loop ring. It's still a 6-pi electron aromatic system. But the double bond is in conjugation, so this is a little bit more stable double bond than normal. But it's not affecting the aromaticity. E1 can also be done because, again, the carbocation is more stable because of resonance. So these can really undergo E1 reactions easily. So none of these reactions that we just talked about are particularly new, except for the oxidation of the benzylic position. We just have to have one hydrogen directly attached to the carbon for that reaction to occur. Which means if you have a benzene ring in your system, you have to be really careful with using chromic acid. Because if you're trying to oxidize an alcohol, you're also going to oxidize in benzylic position. So you have to be careful with it. So let's look at some examples. We can do a couple of transformations. If we look from here to here, we have no functionality on this outside ring, but we have two benzylic positions, so if we use Br2 in light or NBS in heat, then we can get the radical bromination of the benzylic position. Once we have that, we can do an elimination to form double bonds. Notice this reaction is going to be pretty reactive because we form two aromatic rings. We started with one, now we have two aromatic rings. So that reaction is pretty useful. Now these carbons are our benzylic position, so we can use KMnO4 heat to get the carboxylic acids in that position. Again, notice we're not adding any additional carbons. The amount of carbons we started with are the same all over here. If we take this and react to KMnO4 in heat, or our chromic acid, then we're going to get the benzylic positions. Now this is benzylic positions. Everything else that was attached is byproduct. That gets completely clean because we have a hydrogen in both positions. So we can do multiple things with our benzylic position. If we look at this example, we're trying to come up with a plausible synthesis. You might right away say, let's just oxidize it to put chromic acid there, but that's not going to work because our resulting compound is not a carboxylic acid, and we can't stop at the aldehyde using chromic acid or KMnO4 and heat. That's absolutely not going to stop there. So in this case, what can we do? Well, if we put an alcohol in that position, we can use PCC to stop the aldehyde. But this isn't just a simple throw in oxidizing agent to react with the benzylic position. So you might think that, but those two things are not the same. This reaction gives you a carboxylic acid. This is not a carboxylic acid, that's a hydrogen. So instead, what we can do, we can use free radical bromination to add a bromine to that benzylic position. Then we can do one of the substitution reactions to replace the bromine with an alcohol. We can use SN1 or SN2 in this case, depending on our conditions. This one's showing SN2 with our hydroxide because it's not hindered. Now that we have the alcohol, now we can use PCC to stop at the aldehyde. So this route is still not a very long route, but it's a little bit different than what you might have looked at first. So remember, when you're oxidizing your benzylic position with chromic acid or KMnO4, you're going all the way to the carboxylic acid as long as there's a hydrogen in that benzylic position. If we look at this example, well, we're not adding any carbons. So here it looks like we are replacing C-double-bond-O with bromine. We can't outright replace C-double-bond-O with bromine, but what we can do is reduce our ketone to an alcohol. Now remember, well, we haven't really talked about this yet. So we can form our alcohol. Once we have our alcohol, we can do an SN1 or an SN2 reaction to form our bromine. So those are our best routes there. Or HBr. HBr actually makes our alcohol a good leaving group. So that one's a little bit better. Going through the SN1. And again, you can do this SN1 pretty easily because our most stable carbocation is in resonance. Or if you did want to use sodium bromide, you'd have to make alcohol and get the leaving group first. So that's a good route. Now when we are reducing, we're showing lithium aluminum hydride, and we know that's not going to react with double carbon-carbon double bonds anyway. But our next reactions we're going to talk about is reducing the double bonds of the ring. And can we do that? So it turns out, yes, you can reduce the double bonds of the ring. And you must be able to because we were actually using the hydrogenation to understand this stability. But one thing to note, it takes really, really, really harsh conditions to reduce the rings of the double bond. Because even though the final product is more stable, the transition state, which breaks the aromaticity, is really high in energy. So notice these conditions. We're using 100 atm of pressure. That's a lot of pressure. Standard conditions is 1 atm. So this is a lot of pressure. We're putting a lot of pressure in the system and typically a lot of heat. We also need 3 H2 molecules. Usually you'll use excess, but we need at least 3 moles because we're reacting 3 pi bonds. However, if we use typical reducing conditions, the overall process is going to be exothermic because no double bonds is more stable than having double bonds, but it has a really high activation energy. If we use a lot less harsh conditions, it's a lot easier to reduce any double bonds that's not in the ring. So you can actually selectively reduce the double bonds outside of the benzene ring without touching the benzene ring if you use typical conditions, like 2 atm and 25 degrees Celsius. Now remember, these conditions will also reduce aldehydes and ketones and carboxylic acid, so you have to be careful with H2. But we can selectively reduce the double bonds outside of the ring and not touch the ring. With these conditions, if you have any other pi bonds in the molecule, they're all reduced. Whether they're carbon-oxygen double bonds, whether they're carbon-carbon double bonds. If you're using harsher conditions that can reduce the ring, you're reducing everything. So you can't select to reduce just the ring and not reduce anything else, because that takes more conditions. But you can lower those conditions just enough to reduce everything outside of the ring and keep the ring intact. So that makes sense. So what we're usually looking at is much less pressure and much less temperature. This is less harsh conditions. Now in both cases you need the catalyst, platinum, palladium, or nickel. Notice here I have nickel, here I have platinum, that's irrelevant. As long as you have one of the metal catalysts, this will work. But even with catalysis, you still need a lot of energy to break the aromatic ring. There's one last reduction that we're going to talk about today. And this one's a bit special, and we're going to have to really look at the mechanism for this one. So this is called the Birch reaction, another named reaction. Alkenes can be reduced via a dissolving metal reduction. We've seen this before with taking a triple bond and forming the trans double bond. These conditions can also be used to reduce the benzene ring, but what we're going to always form is a net loss of one pi bond, so we're going to retain two of them, and the two pi bonds are going to be across from each other. So that's going to be this particular reaction. So remember, our dissolving metal conditions is sodium metal and NH3, which is not the same as NaNH2. So this is the same conditions. Only we're specifying methanol as a source of hydrogen. But this is the same dissolving metal conditions as when we reduce the triple bond to the trans double bond. So our sodium metal has an electron, and it wants to give it up. It doesn't want to form a covalent bond. It just wants to be Na+. Sodium metal is very reactive. So it gives up its electron, and what it does, that will be formed is a radical anion. And just like with our triple bond, where our radical and our anion wanted to be as far apart as possible, that's still the case here. So in this case, for our radical and our anion to be as far apart as possible, they have to be parallel to each other. So when one electron is given, the ring will reposition itself to have the radical opposite from each other. So what that means is our two pi bonds are going to be opposite from each other, because there's no other way for our radical and our anion to be as far away from each other as possible, and they repel each other. So they're always going to be parallel to each other, which always results in our two double bonds being opposite from each other in the ring. Then, of course, the hydrogen source, our methanol, is going to protonate. We'll have this radical, still not stable, so that will be form an anion from, again, we have more sodium metal floating around. And then we'll have a second hydrogen transfer. So what we're forming is a reduction. It isn't that reduction, we lose one pi bond, but we're always going to form the double bonds across from each other, and what causes that is this. Because our radical and our anion don't want to be near each other. They want to be apart from each other. So we're going to finish this chapter on Monday, because all I want to talk about is if we have functional groups, what our final product's going to be. This is also going to depend on where our double bonds are going to be, based on if we have any R groups attached. So you guys have a good day. I will see you on Wednesday. Yes. How's it going? Everything's good? You can either come right now and do it, or you can wait till this afternoon.
Now's good.
Now's good? Okay, great. Let's go to my office. I'm gonna check and see if the conference room is available. If not, you can do it in my office, but I like to put you in the conference room because it's quieter.
Okay.